Hello everyone, my name is Fardin Bahreini. The title of this paper is Developing Computer Vision-based Digital Twin for Vegetation Management near Power Line Distribution Networks. We'll cover introduction, literature review, proposed framework, implementation and results, and contribution and future work. Let's start with introduction. Vegetation near power lines causes around 40% of outages, especially during severe weathers. Moreover, traditional inspection are labor-intensive, slow, and lack accuracy and frequency. Also, LiDAR and machine learning enhance monitoring with high-resolution spatial data for risk assessment. And digital twins combine real-world data with models to simulate vegetation growth and interaction with power infrastructure. Let's move to problem statement. Manual vegetation management lacks efficiency and accuracy. LiDAR-based methods generate massive point cloud data which cause computational challenges. Moreover, current digital twin models lack integration of LiDAR segmentation with predictive vegetation management. Also, existing proximity detection approaches are static, ignoring dynamics like wind-driven tree motion and seasonal growth. The objectives of this paper are develop a digital twin framework integrating LiDAR segmentation with risk assessment, improve accuracy and efficiency using RandLA-Net for semantic segmentation, also apply KDTree-based spatial analysis to enhance proactive risk management and deliver a scalable solution for real-time monitoring and decision-making in resilient power networks. Let's move to literature review. Digital twins enable timely risk assessment by monitoring tree proximity to power lines. Moreover, dynamic growth simulation help predictive vegetation impact under varying environmental conditions. Also, interference risk can be evaluated, supporting preventative maintenance and system reliability. And integrating species-specific growth models enhance digital twin precision. Let's move to proposed framework. The proposed framework has three main parts: semantic segmentation, post-processing analysis, and digital twin creation, which I will explain each one separately in following slides. Let's start with semantic segmentation and post-processing analysis. RandLA-Net enable efficient segmentation of large-scale point clouds targeting trees, power lines, and poles. Moreover, DBS scan and rule-based thresholding is used to refine segmentation results, isolating significant urban objects. Proximity detection is done using KDTree method for evaluating potential risk based on spatial relationships between tree and power lines. Let's move to digital twin creation for utility lines. For the utility lines, segmented point cloud data imported for processing at first step. Then we did KNN search to estimate normal vectors and curvatures. Then we did radial basis function interpolation to fill the gap between the utility lines. After that, we did upsampling to increase the density of the points, and finally, we did merging and 3D meshing. For the tree and poles, we used the library of the tree and poles model, so we did the registration for 3D model of poles and trees. Then we applied rotation, translation, and scaling to minimize alignment errors with segmented point clouds. After that, we aligned bounding box centers and scaled object based on reference model dimensions. Also, we used iterative closest point algorithm to align 3D models with point cloud data by size and location. Let's move to implementation and results. I will start with data acquisition and preparation. In this study, we used Toronto 3D dataset for the case study, and the dataset was collected through the LiDAR sensors, and each point includes X, Y, Z, RGB intensity, and urban feature classes. We trained the model for 100 epochs using Adam Optimizer. The training took around 124 hours on Lambda stations, and we had 1 GPU and 48 gigabyte RAM. Also, the results was around 97% for trees, 87.44 for power lines, and 82.33 for poles. And this is a sample of point cloud data. As you can see, different objects, including trees, power lines, and poles. Let's move to clustering and rule-based thresholding. DBScan algorithm used to identify clusters of varying shapes and size in complex urban data. Moreover, epsilon and minimum sample carefully adjusted to fit dataset characteristics. Also, we used specific thresholds for urban features like tree and poles to improve differentiation and reduce noise. This table shows the clustering values and defined thresholds that we use for each class. Let's move to proximity detection between trees and power line. KDTree used for different spatial queries to find closest power line points to trees, safety thresholds, assessment flags, trees within risk distance of power lines. Moreover, post-processed data visually highlighted hazardous tree area within 1 meter of lines. This figure shows the results of hazardous tree area. As you can see, the hazardous zone is highlighted in red. These figures show the poles 3D model library and trees 3D model library that we use in this study. Also, for all trees, we assume that all of them are honey locust species. This figure shows an example of gap filling and 3D mesh generation for utility line segments. As you can see, there were uncontinuous problem issue in the point cloud, so we filled the gap with the method that we mentioned. These figures show the service registration for tree and poles. This is the point cloud, and this is the 3D model, and this is the result after the registration. This figure shows a 3D model based on the point cloud data. Let's move to contribution and future work. The contribution of this paper are develop an integrated digital twin framework combining LiDAR-based segmentation and proximity analysis. Moreover, we implemented DBScan clustering and rule-based thresholding to improve segmentation accuracy and reduce noise. Also, we utilized KD-Tree spatial queries for precise risk assessment of hazardous vegetation near power lines, and we provided a scalable solution for enhancing power distribution resilience through proactive vegetation management. Let's move to conclusion and future directions. This study demonstrated how digital twin improve vegetation risk assessment, power reliability, and maintenance planning. Moreover, the proposed framework integrated LiDAR-based segmentation with digital twin modeling, addressing key limitation in existing approaches. Future work should focus on incorporating real-time multi-source data and predictive vegetation growth modeling for better adaptability. And also, optimizing the computational efficiency is needed for real-time processing in large infrastructure network. Thank you for your time.